Hello guys, in this very lesson under chemistry, we're going to be discussing the law of reciprocal propulsion. In our previous set of lessons on the various laws that guide how chemical substances combine, we looked at the law of conservation of mass. We went on also to discuss the law of definite proportion or constant composition before we went on to discuss the law of multiple proportion. So today we are discussing the law of reciprocal propulsion. This very law was propounded by a German chemist known as Benjamin Richter, just 2 major years after the great work by Antoine Lavoisier. That's the scientist that worked on the law of conservation of mass. So don't forget the fact that John Dalton did a very wonderful work on pointing out the quantitative analysis that deals with chemical combination. But before Dalton did that very great job, a major scientist known as Benjamin Richter did a wonderful job by showing how chemical substances combine in ratio format. And that very scientist is the person we're going to discuss today, and the person of Benjamin Richter. So, what does this very law state? The law of reciprocal proportion states that this states that when elements, it states that when elements A and B, it states that when elements A and B combine, when elements A and B combine individually, when element A and B combine individually with an element C, they do so, in a ratio format. They do so in a ratio format that is reciprocal, or the same, as when they combine. When we talk about they, we're talking about element A and B, as when they combine directly. Now, this is what Benjamin Richter is talking about. Benjamin Richter is a German scientist. Before John Dalton came on board, before James Louis Pratt came on board, Benjamin Richter, a German scientist, did a wonderful job, as per explaining how various chemical substances combine on a quantitative note. So it was said that provided we have a major element A and element B, or we have a major, let's say, compound A and compound B. So by the time this very major element A and B combine together, if we check the ratio at which they combine together, if we draw a kind of comparison between the ratio of that direct combination, is the same ratio as when each of these elements combine with element C individually. That's what Benjamin Richter observed while he was carrying out a major experiment. Now, this very work was what James Louis Pratt and John Dalton beat on. So we're going to be looking at a couple of examples, 2 major examples. So first of all, we're going to be looking at this. We are going to be looking at this 2 major elements. This first major example, you have hydrogen, you have oxygen, hydrogen, oxygen combining with sulfur. So we're going to be looking at this first. Hydrogen, oxygen, and sulfur combining. Now, the 2 major players here are hydrogen and oxygen. Now, when hydrogen and oxygen combine together, if you look at the ratio of combination, now we're going to be comparing the ratio of combination, when it comes to hydrogen combining with sulfur and oxygen combining with sulfur. So we're going to be doing that. First of all, hydrogen and oxygen, let's look at that. Hydrogen plus oxygen having a combination. Now, hydrogen naturally has a valency of 1. Oxygen has a valency of 2. So let's see what we're going to get. Hydrogen plus oxygen will give us H2O, that is H2O1. So this is water. So what do we have from here? H2O, that is, we have 2 grams of hydrogen plus, what's the atomic mass of oxygen? Plus 16 grams of oxygen. So when we have a ratio, when we compare this, that's 2:16, which gives us 1:8. So when hydrogen and oxygen combines directly, we end up with 1:8. By the time you compare their masses together. So now, don't forget, if hydrogen combines with sulfur and then oxygen combines with sulfur, by the time we compare them, according to Benjamin Richter, the German chemist, we're still going to get the same 1:8. So let's work on that. Let's interpret that. Hydrogen and sulfur combining. Let's see if they combine individually with element C. Then we compare them. Let's see if they're going to get the same ratio of combination. So hydrogen plus sulfur. Hydrogen at valency 1, sulfur has you have the kind of sulfur, but the sulfur we're going to be dealing with now is just the sulfur, this 2 here, the sulfur 2. So what do we have? We cross multiply. You have H2 and S1. That's what we have. So H2S1, this hydrogen sulfide. So hydrogen here is 2 gram. We're going to compare. Then sulfur here has an atomic mass unit of 32. So when we combine them, that is 2 year 1, 2 year 16. So hydrogen and sulfur, that's hydrogen sulfide, give us 1:16. That's what hydrogen and sulfur will give to us, 1:16. So this is hydrogen and this is sulfur. So the next thing we're going to do now, we're going to combine oxygen and sulfur together. Oxygen and sulfur. So let's quickly do that. Oxygen plus sulfur, that is sulfur plus oxygen. Now the sulfur we are talking about here, don't forget the sulfur 2 we are talking about here. So since you're talking about sulfur 2, so sulfur here 2, oxygen here naturally is 2. Valency of 2 each. So we cross multiply, we have S2O2. When we break them down, we have sulfur monoxide. Now, sulfur monoxide is a kind of gas that is not common. It's an astral gas under astrophysics. This gas is mainly found in Jupiter and Venus. So when it comes to planet Earth, this gas becomes S2O2, disulfur dioxide. That's what we're going to have, but it's mainly found in space in Jupiter and in Venus. That's why we have this SO. So this sulfur monoxide. So how do we compare this? The sulfur here is 32 gram, oxygen here is 16. When we break them down, 16 year 1, 16 year 2. What do we have? We have 2:1. So as you can see, we have a 1:16 here, we have 2:1. By the time you compare them, 16 and 2, this 1:1. So 1:16, 2:1. By the time you compare them, we end up with, this is what we're going to end up with. We're going to end up with 2:16. To break them down, 2 year 1, 2 year 8 is the same thing as 1:8. As simple as that. It's the same thing as when hydrogen and oxygen combines directly. When hydrogen and oxygen combines directly, we're going to end up having 1:8 as per, the ratio of the masses. So, but when hydrogen combines separately with sulfur, as you can see, when we did that, we got 1:16. And when sulfur combines separately with oxygen, we also got, we got 2:1. So by the time we compare the bunch of ratios, now don't forget, sulfur here, 1:8, and sulfur here is 2:1. So sulfur, by the time we combine them, since hydrogen and oxygen combines individually with sulfur, we end up with 2:16, which is 1:8, which is the same thing as when they combine, directly. So this is what the law of reciprocal proportion is all about. When two major players, elements such as hydrogen and oxygen, combine individually with a third party element, the ratio at which they combine is the same as when they combine directly. This is all Benjamin Richter talked about in his major law of reciprocal proportion. So either they combine directly or they combine with third party element, is still going to be the same ratio of combination. It's as simple as that. So at this very point, we're drawing the curtain on this very lesson. I'd love you to give me other forms of examples, other forms of chemical reaction that obey the law of reciprocal proportion. We have a couple of other ones. We have carbon, oxygen, and sulfur. When carbon and oxygen combines together directly, you have a given ratio of combination. When they combine with a third party element called sulfur, we still have the same, by the time you compare them, we end up having the same ratio of proportion. So carbon, oxygen, and sulfur, it's another example, but I'll allow you to give me your own examples in the comment section. So we're drawing the content on this very lesson. So if you found this lesson helpful or resourceful, please subscribe to this very channel at Edge Mosaic, and please give me a follow or revelation on Facebook. So I'll see you in the next class. Thanks.